Section 3 of the physiology handout, then, is the peripheral circulation. Now, the questions they have in Step 1 in the peripheral circulation are usually very basic questions. They just want to see if you understand the basic concepts. There's very little detail in their questions here. And if you follow me through and get a good handle on the concepts here, you should not have a problem with the questions on Step 1. However, I would like to point out that some of these questions are not considered easy questions. They're very basic questions, but they're not necessarily easy questions. Now, we start off the section by looking at a diagrammatic representation of the entire cardiovascular system. Now, this figure here is a diagrammatic representation of the entire cardiovascular system. And the main point of this figure is to demonstrate that the right heart, the pulmonary circuit, the left heart, and the systemic circuit are all connected in series. Now, when structures are connected in series, they are connected end to end. And you have to understand that all four structures here are connected in series. Now, the big point is, when structures are connected in series, you have to accept that the flow must be the same at all points in that series system. Therefore, then, if I told you the output of the left heart was 5 liters per minute, you have to accept that the flow through the systemic circuit is also 5 liters per minute. The output of the right heart is also 5 liters per minute, and pulmonary flow is also 5 liters per minute. If you know the flow at any point in a series system, you know it at all points because the flow must be the same. Now, if I told you that a person exercises and the output of the left heart went from 5 liters per minute to 15 liters per minute, you should be able to conclude the pulmonary blood flow during this exercise session must also be 15 liters per minute because the flow is the same at all points in a series system. Now, there's 3 really standard basic questions about what we just went through here. The first basic question simply asks, what does the systemic circuit have in common with the pulmonary circuit? And we can list various parameters such as pressure, capacitance, resistance, and we have to list flow because the only thing the pulmonary circuit and systemic circuit have in common is flow. In a normal person, the flow is the same in the 2 circuits. Now, another standard question is to simply ask you, what is the ratio of flow in the pulmonary circuit to blood flow in the systemic circuit? That ratio should always be 1.0 in a normal individual because it must be the same. It is 1.0 under resting conditions. It is still 1.0 during exercise because flow changes equally in the 2 circuits. Now, this would be the best question of the 3. We could also ask what percentage of cardiac output flows through the pulmonary arteries. And you should realize it must be 100% because by definition, the output of either heart is cardiac output. Cardiac output is not only the output of the left heart, it is the same output as the right heart. It's the same as pulmonary blood flow. That is just testing that this is a series system. Now, another point that is also important here is to realize that the composition of pulmonary venous blood is the same composition as systemic arterial blood. That's a very important point to remember. When blood leaves a pulmonary capillary, it does not change its composition significantly between that point through the left side of the heart until it gets to the systemic capillaries. So pulmonary venous blood is more or less the same composition as systemic arterial. In addition, you should also realize that systemic venous blood has the same composition as pulmonary arterial blood. There are no significant differences between the composition of blood flowing into the right heart and flowing through the pulmonary arterial system. In fact, a very good basic question in cardiovascular or peripheral circulation is to simply ask you which artery in the entire cardiovascular system has the lowest PO2. Now, most people associate arteries with a high PO2, but obviously you should realize the pulmonary artery has a low PO2. That's a very good basic question. Now, at this point, we're going to forget about the pulmonary circuit and we're going to focus on the systemic circuit. And what I want to do next specifically is to go through characteristics of the systemic circuit. But in your notes, you'll realize there is a table here that has the basic parameters in the pulmonary circuit versus the systemic circuit. This is just for your reference. We're not going to go through this, and you should not memorize those numbers. Now, as I said, I want to focus on structure-function relationships in the systemic circuit. Now, this figure is put in the handout just to illustrate that the systemic circuit is a branching circuit. You start with one large aorta. It branches progressively until we reach the capillaries where the branching reaches a maximum. And then as you go through the venous system, you have the opposite then. The system comes back together to a couple of vena cava that enter the right side of the heart. Now, what we're going to do specifically here is to follow specific parameters as we move through the systemic circuit. Now, the first one we are going to consider is pressure. And this is a very important graph to totally understand. And we'll add some details as we go through here. Now, this graph simply shows what happens to pressure as we go through the systemic circuit. Now, we're assuming the person is lying down, and therefore there is no effect of gravity. We're starting in the aorta where the mean pressure is about 100. And we're simply going to follow this pressure as we move through the systemic circuit. Now, I know there is a phasic pressure pattern in the arteries. We're not going to worry about this phasic pattern. We're only going to follow the mean pressure as we go through the systemic circuit. Now, the big point here is, as you go through the systemic circuit, pressure progressively decreases. And what you have to understand is you lose pressure overcoming resistance. The pressure is the energy that is moving the blood through the systemic circuit, and you lose your energy. You lose your pressure overcoming resistance. More specifically, if a segment is a low resistance segment, you lose very little pressure going through that segment. Because if it's low resistance, you don't use up much of your energy. On the other hand, if a segment has high resistance, you lose lots of pressure. If it has high resistance, you have to use up a lot of your energy to move the blood through that segment. Now, what we're going to do here is we're going to go through, and I will point out observations about what we record in terms of pressure changing. And once we look at that observation, we will draw a conclusion about the resistance of that particular segment. Now, looking at the figure here, and don't forget this person is lying down, and we don't have the effect of gravity. As you go through the systemic arteries from the aorta to the smaller peripheral arteries, what we observe is very little decrease in pressure. Now, because we observe only a small drop in pressure, we conclude that the major arteries must be a low resistance system then. So because the major arteries lose very little pressure, they represent a low resistance pathway. That means it doesn't matter where you measure a patient's blood pressure, as long as the artery is at heart level. You record the same approximate pressure in any artery at heart level. It's simply because arteries are a low resistance pathway. Now, the next observation involves the arterioles. Now, what we observe here is, as we go across the arterioles, we have a huge drop in pressure. In fact, you should realize you'll lose most of your pressure passing through the arterioles. Now, because you'll lose most of your pressure going through the arterioles, you have to conclude the arterioles represent a high resistance segment of the systemic circuit. We can go one step further. Because we observe most of our pressure being lost as we go through the arterioles, it must mean that the arterioles here represent the highest resistance segment of the systemic circuit. Now, as we continue through the capillaries, we will lose a modest amount of pressure here. Therefore, the capillaries represent some resistance, but not a huge resistance. You lose a modest amount of pressure going through the capillaries, so they do have some resistance. Now, the last important point here is what is happening in the venous system. Now, what we observe is, as you pass through the venous system, there's very little decrease in pressure. That means the veins represent a very low resistance pathway. There's three big points to remember from this figure so far. First of all, the major arteries are a low resistance pathway. The arterioles represent the highest resistance segment of the systemic circuit, and the veins, like the arteries, represent a low resistance pathway. Now, just extending this information slightly, and again, this is really important to understand. The arterioles are used to control the flow in the capillaries. We can alter the resistance of individual arterioles. Now, what we're going to consider next will be the consequences of changing the resistance in a single distal arteriole. Now, the reason we're only considering a single arteriole is because when I change the resistance in a single arteriole, then I will not change blood pressure. So we're going to consider blood pressure to be constant at 100 millimeters of mercury, and when we change the resistance of a single arteriole, we will summarize the effects downstream in the capillaries. So when we change the resistance of the arterioles here, we're going to look downstream for consequences in the capillaries. Now, just follow me through on this, but it should make sense when you put it all together. If you dilate an arteriole, everyone will accept that the resistance of that arteriole decreases. Now, if it decreases, then you will conclude there's more flow downstream in the capillaries. Now, if you dilate the arteriole, there will definitely be more flow downstream in the capillaries. But this is the additional point that's important. if you dilate an arteriole, because it is now a lower resistance pathway, you lose less pressure going through. So let me repeat that. Because an arteriole is now a lower resistance pathway, you will lose less pressure going through the arteriole, which means if you look downstream in the capillaries, there will be more pressure. The bottom line is, when you dilate an arteriole, downstream in the capillaries, you not only get more flow, but you also get more pressure. You cannot independently regulate flow and pressure downstream in the capillaries. Now, if we consider the reverse situation, suppose you constrict an arteriole. If you constrict an arteriole, you increase that arteriole's resistance. And most people will accept readily that downstream in the capillaries, there's less flow. But again, the additional point is, if you constrict an arteriole, then that arteriole has more resistance. And if it has more resistance, you'll lose more pressure getting that blood through that arteriole. So downstream in the capillaries, then, you have less pressure. So just summarizing that then, if you constrict an arteriole downstream, there's not only less flow, there is less pressure. Okay? There's less flow and less pressure. Okay? The next parameter to consider is cross-sectional area. And by cross-sectional area, we mean the total cross-sectional area of all vessels in a particular segment. So again, going through the systemic circuit, if we start in the aorta. Now, the aorta is a large vessel, but it is only one vessel. And because it is only one vessel, it represents the smallest cross-sectional area of the systemic circuit. It is important to remember that the aorta is the smallest cross-sectional area of the systemic circuit. Now, as we move peripherally through the arterial system, an individual vessel has a smaller cross-sectional area, but collectively the cross-sectional area increases. It progressively increases until we reach the capillaries. Even though a single capillary has a small cross-sectional area, taken collectively, the capillaries represent the greatest cross-sectional area of the systemic circuit. And as we proceed beyond the capillaries, then, the cross-sectional area progressively decreases until we get into the vena cava, where again it reaches a fairly low level, but it does not reach the very low level that we started with in the aorta. Again, there's just a few points that are important here. The aorta represents the section of the systemic circuit with the smallest cross-sectional area. It increases progressively to reach a maximum in the capillaries, and then it decreases progressively as you go through the systemic veins. Now, the next parameter is velocity, and it doesn't matter what hemodynamic system we are considering. There is always an inverse relationship between cross-sectional area and velocity. Now, be careful here. Velocity is speed. It is not flow. Velocity is measured as distance per unit time. Flow is measured in volume per unit time. So we're only considering the parameter of velocity. Now, because of this inverse relationship, then, because the aorta has the smallest cross-sectional area, it has the greatest velocity. Very big point to remember. Because the aorta has the smallest cross-sectional area, it has the greatest velocity. Now, as we proceed peripherally, because the cross-sectional area increases, velocity progressively decreases. It reaches a minimum in the capillaries, and then it progressively increases as you go through the venous system back towards the right side of the heart. Now, the last parameter we have to consider here is blood volume. Now, we didn't put the graph in because there's only a couple of points that are very important here. First of all, the largest blood volume of the entire cardiovascular system is in the systemic veins. And they do test the point that the greatest volume of blood is in the systemic veins. It represents your largest blood reservoir in the cardiovascular system. The second largest blood volume, your second largest reservoir, is the entire pulmonary system. Both the pulmonary arterial and the pulmonary venous system store a significant amount of blood. So in terms of your reservoirs then, the systemic veins represent your largest blood reservoir. The pulmonary circuit is your second largest reservoir, but both represent major blood reservoirs. Now, that's all we need to deal with in terms of individual parameters. The next topic here is hemodynamics. Now, people get a little intimidated with the hemodynamic section because it's a little bit more mathematical. Now, as I said earlier, we try and reduce the mathematics to a minimum, but we do have to deal fairly extensively with the Poiseuille equation. Now, there's different formats for the Poiseuille equation. This is the format we're going to start with. And all this equation states is that the flow through a particular hemodynamic system depends upon three parameters. P1 is the pressure at the beginning of the circuit. P2 is the pressure at the end of the circuit. And P1 minus P2 is the pressure gradient. This is the net force that is pushing the fluid through the hemodynamic system. And the third parameter is the resistance of all vessels between P1 and P2. Resistance impedes the flow, and that is the third parameter. Now, this equation can be applied to a single vessel, a single tissue or organ in the systemic circuit, or the entire systemic circuit, or the entire pulmonary circuit. Now, what we're going to do next here is simply apply this equation to a single vessel. So this equation simply states that the flow through this single vessel here will depend upon P1, which is the pressure at the beginning of the system, minus P2, which is the pressure at the end of the system. And as I said, the difference is the pressure gradient. It is the net force forcing the fluid through the system divided by the resistance of this tube between P1 and P2. And this equation can be applied to any hemodynamic system. Now, what we're going to do next is to take a look at individual parameters that determine the resistance of a tube or an entire system. Now, this does not represent the entire system. We're only going to look at parameters that are important for step one. First of all, they can test your understanding of resistance units. Now, nobody memorizes resistance units, and therefore you have to use the Poiseuille equation to figure out appropriate resistance units. Now, this is the Poiseuille equation just reformulated, so we have resistance on the left, and therefore this form of the equation tells you that resistance equals pressure divided by flow. Therefore, then, units of resistance will be pressure units divided by flow units. Typical pressure units are millimeters of mercury, and flow units can be mils per minute. Therefore, then, resistance units are simply pressure units divided by volume units divided by time units. So on the exam, they can give you a question where they list 5 different units and ask you which of the following units is appropriate for measuring resistance. You simply look for pressure divided by volume divided by time. And if you can't remember that, you just reorganize the Poiseuille equation and you read it from the equation. Now, if we look at specific parameters that determine the resistance of a tube or a vessel, These are the only three that are important for step one. And of these three, the most important parameter is the radius of the tube. And you should realize the resistance is inversely proportional, not just to the radius, but to the fourth power of the radius. Therefore, then, the arterioles, which are the main regulators of flow distribution and make up the greatest component of TPR, their resistance is determined mainly by the radius of the arterioles. The most important factor determining resistance is vessel radius. And resistance is inversely proportional not just to the radius, but it's to the fourth power of the radius. So the resistance of an individual tube is mainly determined by the radius of that tube. Now, looking at the arterioles, which are the main regulators of flow distribution and make up the greatest component of TPR, you should realize the resistance of the arterioles is mainly determined by their radius. Therefore, then, we regulate total peripheral resistance by basically regulating the radius of the arterioles then. So you regulate total peripheral resistance by simply regulating the resistance of the arterioles. Because it's to the fourth power then, a very small change in radius can produce a huge change in resistance. Now, they can get quantitative on the exam, and because it's to the fourth power, it's 2 times 2 times 2 times 2 for doubling, etc. So the number you memorize is 16. Therefore, if the radius is decreased to 1/2 of the original, the resistance increases 16 times. On the other hand, if the radius doubles, then the resistance will decrease to 1/16 of the original. And that is the most important factor determining resistance. Now, a second factor is blood viscosity. And resistance of any hemodynamic system will be proportional to blood viscosity. Now, hematocrit will affect viscosity. This is a normal situation here where you have a hematocrit of around 40%. Now, if you develop anemia, this will decrease viscosity. And because viscosity is decreased, the total resistance of the cardiovascular system decreases. If you decrease hematocrit, then it is easier to pump the blood through the systemic circuit. So as you develop anemia, because resistance goes down, it is easier to pump the blood through the cardiovascular system. More importantly for step one, if you develop polycythemia, viscosity increases and therefore resistance increases. In polycythemia, it is more difficult to pump that blood through the cardiovascular system. It requires much more energy. And that is the point more likely to be tested on step one. Now finally here, and this is a smaller point, but resistance is proportional to the length of an individual tube. The greater the length of the tube, the greater the resistance. Now again here, they can ask a question that is fairly quantitative. And you should realize if the length of a tube doubles, its resistance will double. On the other hand, if the length of the tube decreases by 1/2, then the resistance will decrease by 1/2. Now there are other variables that determine resistance, but these are the only variables they will test on step one. Now the next topic is laminar versus turbulent flow. Now any hemodynamic system will have either a laminar flow system or a turbulent flow system. Now by definition, laminar flow is flow in layers. And they could ask you to define laminar flow on an exam, and it's simply flow in layers as presented on this figure here. Now, there's two major characteristics that you have to remember. In the normal cardiovascular system, excluding the heart, you have laminar flow. And laminar flow is silent flow. Therefore, then, if you put a stethoscope up to a vessel that has laminar flow, which is the normal situation, you hear nothing. The other characteristic, and it's a very minor point, even though flow is layered, not all of the layers have the same velocity. The layer with the highest velocity is in the center of the tube.